Derivatives of trigonometric functions. We have two important limits that we need to know. The first states that if we take the limit as theta approaches 0 of sine of theta divided by theta, this limit is equal to 1. The second one is the limit as theta approaches 0 of cosine of theta minus 1 over theta is equal to 0. This first limit requires a geometric proof, which I am going to skip at this time, and the second limit can be shown easily if we assume the first limit is true. I'm not going to prove either one of these limits, as the proofs for these are readily available. Let's get into what's important. What is the derivative of f of x equals the sine of x? To compute this derivative, we will use the definition of a derivative. So this is going to equal the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. And to finish this, we need to remember one of our identities from trigonometry. And it is the following. If you have the sine of angle A plus angle B, this is equal to the sine of A times the cosine of B plus the sine of B times the cosine of A. And so if we apply this with A being x and with B being h, we have that the sine of x plus h is equal to the sine of x times the cosine of h plus the sine of h times the cosine of x. And so now let's just substitute that expression into here. And so here is what we get. And now what I'm going to do is take this fraction and break it apart into the sum of two fractions. In the first fraction, I'm going to have this term minus this term over h, and in the second fraction, we'll have this term all by itself. And so here is what we get when we break this up. And now I'm going to use a property of limits, which says that I can take the limit of the first fraction plus the limit of the second fraction. And now to evaluate this limit, what I'm going to do in this first limit is factor out sine of x. And in the second limit, I'm going to factor out cosine of x. And I can do this because x is independent from h. And so here is the intermediate step. And now, like I said, since x is independent of h, we're going to pull sine of x out of that limit, and we're going to pull cosine of x out of that limit. And when we do that, we get the following. And now we come to the point where we're going to use those limits in the beginning. So let's remember that the limit here is equal to 0. And let's also keep in mind that this variable theta could be any variable. So it could very well be h here, and h here. And I want you to notice that this is exactly the limit that we have right here. So this limit is equal to 0. And the other limit right here is equal to 1 for the same reason. So we can see up here that if we take the limit here as h goes to 0 of sine of h over h, we get 1. And so now to complete this, what we have here is sine of x times 0 plus cosine of x times 1. And of course, sine of x times 0 is 0. And cosine of x times 1 is cosine of x. So we've answered the question, what is the derivative of sine of x? It is cosine of x. Now let's take a look as to why this makes sense. So here we have the graph of f of x is equal to sine of x. And here is the graph of the derivative, which is cosine of x. And just notice that on the sine graph, everywhere you have a horizontal tangent line, of course the slope of that tangent line is 0. So the slopes of all of these horizontal tangents are all 0. And I want you to notice at those same x values, cosine is equal to 0 at those points. Also, notice from this point to this point, the slope of any tangent line for sine is going to be a positive number. And I want you to notice that on the cosine graph between this point and this point, the values of cosine are all positive numbers. Likewise, if we go from here to here on the sine graph, the slope of any tangent line between these 2 points is clearly negative. And notice that the values of the cosine function are also negative. So this is a way of graphically seeing that it makes sense that the derivative of sine is cosine. Now let's talk about the remaining derivatives. Using similar techniques, if f of x is cosine of x, we can show that the derivative is negative sine of x. I will leave this as an exercise for you because you prove it pretty much the exact same way that we just did sine of x. Let's talk about tangent. So if f of x is equal to tangent of x, what is its derivative? Now we're going to use a slightly different technique here. So let's start with f of x is equal to tangent of x. And let's remember that we can rewrite this as the sine of x divided by the cosine of x. And now if I want to know the derivative of tangent, I can simply apply the quotient rule to this fraction. And we can do this because we now know the derivative of sine is cosine and the derivative of cosine is negative sine. So applying the the quotient rule, the derivative here is going to be the bottom function cosine multiplied by the derivative of the top function minus, and then we'll take the derivative of the bottom function and multiply that by the top function, all divided by the bottom function squared. So now let's just compute these derivatives. We have cosine of x multiplied by the derivative of sine of x, which is cosine of x. Then we have minus the derivative of cosine of x, which is negative sine of x, and then times sine of x, all divided by cosine squared of x. Now if we just simplify this, cosine times cosine is cosine squared. When you subtract a negative, you get a positive. Sine times sine is sine squared. And now let's remember one of our most fundamental trigonometric identities, which is cosine squared of x plus sine squared of x is equal to 1. So this becomes 1 divided by cosine squared of x. Now, this is the same as 1 over cosine of x quantity squared. But 1 over cosine is secant. And secant quantity squared is secant squared. So we now know that if f of x is tangent of x, f prime of x is secant squared of x. In a similar manner, we can show that if f of x is cotangent of x, its derivative is negative cosecant squared of x. You pretty much follow the procedure that we just outlined. So now, what about secant of x? What is the derivative of secant of x? So to answer this question, let's just remember that if f of x is secant of x, we can rewrite this as 1 divided by the cosine of x. And now if I want to find the derivative, I can simply use the quotient rule. Quotient rule says to take the bottom function, cosine, multiply it by the derivative of the top function. The top function is 1, so we're taking the derivative of 1, minus, and then we take the top function times the derivative of the bottom function. So the derivative of cosine multiplied by 1. All divided by cosine of x quantity squared. Now let's do the math on this. We have cosine of x multiplied by the derivative of 1, which is 0, minus, and then we've got the derivative of cosine, which is negative sine, multiplied by 1, all divided by cosine squared of x. Cosine of x times 0 is 0, so we have negative sine of x, which is sine of x. And then in the denominator, I'm going to rewrite this as cosine times cosine. And then I'm going to pull apart this fraction to write it like 1 over cosine times sine over cosine. And 1 over cosine is the secant, and sine over cosine is the tangent. And so the derivative of secant of x is secant of x times tangent of x. And in a similar way, if our function is cosecant of x, its derivative can be shown to be negative cosecant of x times cotangent of x. So let's go ahead and summarize all these derivatives. So here are the derivatives of the 6 trigonometric functions. And I want you to notice that there is a pattern involved. So starting with sine and cosine, the derivative of sine is cosine. The derivative of cosine is negative. And then what is the co-function of cosine? Well, it's sine. Similarly, the derivative of tangent is secant squared. Jump down to the bottom here. The derivative of cotangent is negative. And then what is the co-function of secant? Well, it's cosecant. So I want you to notice that these two derivatives are very similar to each other. It's just that one is positive, the other is negative, and then secant and cosecant are co-functions of each other. And then likewise, the derivative of secant is secant times tangent, and the derivative of cosecant is negative cosecant cotangent. So this derivative and this derivative, again, have the same pattern. So the derivatives of all of the regular trig functions, sine, tangent, and secant, are all positive, and the derivative of all of the co-functions are all negative. And knowing this and knowing the patterns can help you remember these functions. And you need to memorize these because you do not want to have to figure these out when you need to use them. Now let's take a look at some examples involving taking derivatives of trig functions. So in the first example here, we want to differentiate y equals x squared times the sine of x. So I'll just remind you that this is a product rule because we are multiplying two functions together. And so the derivative dy dx will be the first function, x squared, multiplied by the derivative of the second function, so derivative of sine of x, plus, and then we'll take the derivative of the first function multiplied by the second function. So if we do the math on this, we get x squared times the derivative of sine is cosine, plus the derivative of x squared is 2x times sine. And so this is the derivative. Now, you can actually factor out an x here, and so sometimes you'll see the answer expressed in this way. But both of these are correct. In the next example, we're asked to take the derivative of this function, and then we're also asked for what values of x does the graph of f have a horizontal tangent. So first, let's go ahead and find the derivative. So if f of x is equal to secant of x divided by 1 plus tangent of x. To find the derivative, we're just going to use the quotient rule. And the quotient rule says to take the bottom function and multiply it by the derivative of the top function minus, and then we'll take the derivative of the bottom function and multiply it by the top function, all divided by the bottom function squared. Now, if we do the math on this, we get 1 plus tangent of x multiplied by the derivative of secant, which is secant of x, tangent of x, minus, and then we have 1 plus tangent of x, derivative of that, so the derivative of 1 is 0. Derivative of tangent is secant squared. So we have secant squared of x, and then multiplied by secant of x, all divided by the bottom function squared. Now let's go ahead and simplify further. So in the numerator here, we can multiply this out. So 1 times secant tangent is going to be secant tangent. And then we have tangent times secant tangent, which will be, first of all, positive, and then secant x, tangent squared x, and then minus secant squared times secant is secant cubed. Okay, now we need to simplify, and this is where things can get a little bit tricky. But one thing I want you to notice that we can do immediately is we can factor out secant of x, because we have a secant of x in each of these three terms. So if we pull out a secant, we get secant of x times tangent of x plus tangent squared of x minus secant squared of x, all over 1 plus tangent of x, quantity squared. Now what I'm going to do is apply a Pythagorean identity. So we're going to need to remember that secant squared of x is equal to 1 plus tangent squared of x. So if I do that in the numerator, I end up getting secant of x times tangent of x plus tangent squared of x minus secant squared, which is 1 plus tangent squared. And then now when I distribute the negative here, I want you to notice that this becomes a negative 1, and this becomes a negative tangent squared. And once we do that step, we can see that positive tangent squared and negative tangent squared cancel each other out. And so we end up getting secant of x times tangent of x minus 1 divided by 1 plus tangent of x quantity squared. So this is our derivative. So now let's answer the second part of the question. For what values of x does the graph of f have a horizontal tangent? So remember, a horizontal tangent to the graph of f of x means that the derivative of f of x has to be 0. So that means that this function here, secant of x times tangent of x minus 1 divided by 1 plus tangent of x quantity squared must be 0. And now we need to remember the only way a fraction can be 0 is if the numerator of the fraction is 0. So this means that either secant is 0 or tangent of x minus 1 is 0. Now, let's remember that secant can never be 0. And this is because if you graph the secant function, it looks something like this. And so let's just remember that secant never crosses the x-axis. So that means it cannot be 0. So then tangent of x minus 1 has to be 0. And this means that tangent of x must be equal to 1. Now for this, we need to recall when this is true. So we should know that for one value this is true for is pi over 4, we should all know that tangent of pi over 4 is equal to 1. And then the solutions to a tangent equation are always periodic with a period of pi. So I can add any multiple of pi to this, and this would give me another value of x for which tangent is equal to 1. So the solutions are all the values x equal to pi over 4 plus k times pi, and the number k can be any integer. Next, let's take the derivative of the function g of x equals 3x plus x squared times cosine of x. So g prime of x, we're going to start by taking the derivative of 3x, which of course is just 3, plus, and then here we have a product rule. So we'll take the first function x squared multiplied by the derivative of the second function cosine of x, plus, and then the derivative of x squared multiplied by cosine of x. If we do the math, we have 3 plus x squared times derivative of cosine is negative sine, plus the derivative of x squared is 2x times cosine of x. And then one last step here, let's make sure we clean this up. This negative can go in front here, and this becomes negative x squared times sine of x, plus the rest. So here is the derivative of g of x. In the next example, we find the equation of a tangent line to a curve at a given point. So the function is y equals 1 plus sine of x all over cosine of x, and the point of tangency is x equals pi and y equals negative 1. And just to remind you, they don't have to give you the y value, right? Because we know that if we plug the x value of pi in, the y value would be 1 plus the sine of pi divided by the cosine of pi. And this would be 1 plus 0 divided by negative 1, which is negative 1. So again, they don't have to give you the y value. You could always figure that out, but it's kind of nice when they do. So we start by using the quotient rule to find the derivative. dy dx equals the bottom function cosine of x multiplied by the derivative of the top function minus the derivative of the bottom function multiplied by the top function, all divided by the bottom function squared. If we do the math on this, we get cosine of x times cosine of x minus the derivative of cosine of x, which is negative sine of x, times 1 plus sine of x, all divided by cosine squared of x. So let's go ahead and simplify a little more. This is equal to cosine times cosine, is cosine squared. Then we have plus sine of x multiplied by 1 plus sine of x, all divided by cosine squared. Now we're not finding the derivative as a function so much as we are finding the derivative to find the slope of the tangent line. So you don't have to simplify this anymore. You could just take x equals pi and plug it into your derivative to find your slope. But a lot of times you will want to simplify. So I'm going to go ahead and simplify this a little bit more. We have cosine squared plus sine of x times 1, which is sine of x, plus, and then we have sine of x times sine of x, which is sine squared of x, all over cosine squared of x. And then let's just remind ourselves that cosine squared plus sine squared is equal to 1. And so this is 1 plus sine of x on top and cosine squared of x in the denominator. And again, this is the derivative dy dx. So the slope of our tangent line is going to be this derivative evaluated when x equals pi. And that is 1 plus the sine of pi divided by cosine of pi quantity squared. So remember, when you're squaring a trig function like this, it can be helpful to think of it in this way. Now, we know that sine of pi is 0 and cosine of pi is -1. And so we end up getting 1 divided by 1, which is 1. So now for the equation of the tangent line, we have a slope equal to 1, and we have the point pi -1. And so the equation of the tangent line is y minus -1 equals 1 times x minus pi. And this is y plus 1 equals x minus pi. And if we subtract 1 from both sides, we get y equals x minus pi minus 1. In our next example, we have a function f of t equals secant of t, and we want to find the second derivative of f evaluated at pi over 4. So one thing to keep in mind is plugging in the value pi over 4 is the last thing you will do. First, we need to find the derivative f double prime. So we'll start with taking the derivative of f, and since f is equal to secant, we know the derivative of secant is secant tangent. So the derivative of secant of t is secant of t times tangent of t. Now on to the second derivative. Since our first derivative is a product of two functions, to find the second derivative, we have to use the product rule. So here we're going to take the first function, secant of t, multiplied by the derivative of tangent of t, plus, and then the derivative of secant of t multiplied by tangent of t. And so this is secant of t times secant squared of t, plus the derivative of secant is secant tangent, and then times another tangent. And so this becomes secant cubed of t plus secant of t times tangent squared of t. And this is suitable for what we want to do, which is plug pi over 4 into our second derivative. So now we'll just replace every t we see with pi over 4. So this becomes secant cubed of pi over 4 plus secant of pi over 4 times tangent squared of pi over 4. And to complete this, we need to remember what is the secant of pi over 4 and what is the tangent of pi over 4. Well, tangent of pi over 4 is 1. Secant of pi over 4 turns out to be the square root of 2. And if you need to review these, I would encourage that you do that, because knowing your basic trigonometric values of your basic special angles, such as pi over 4, pi over 3, and pi over 6, these are really important in calculus. So let's finish this. So secant of pi over 4 is the square root of 2, and then we have to cube that because it's secant cubed, plus secant of pi over 4, again, is square root of 2, and then tangent of pi over 4 is 1, and we are squaring that. So what you have here is radical 2 cubed, which is radical 2 times radical 2 times radical 2. Radical 2 times radical 2 is 2, and so we can think of this as 2 radical 2, plus, and then radical 2 times 1 squared is radical 2, and this is 2 radical 2 plus 1 radical 2, which is 3 radical 2. Now let's come back to this very important limit that we mentioned at the beginning of this lesson. First of all, it is true that if the limit of sine of theta over theta as theta goes to 0 is 1, we can basically replace theta with anything that also goes to 0. So for example, I could say the limit of sine of 5x divided by 5x, this would also be 1 as long as x is approaching 0. So this limit is always equal to 1 as long as both of these are the same and as long as that quantity is going to 0. And it should be sort of obvious that if x goes to 0, 5x also is going to 0. And we can use this fact to simplify some other limits. Let's do an example. So if I'm asked to find the limit as x goes to 0 of sine of 7x over 4x, first of all, we can't apply this limit because 7x and 4x are different. But what we can do is we can algebraically manipulate this expression. So let's think about this. If I have sine of x over 4x, what I really need down here is I need a 7 in front of that x. So what I'm going to do is pull that 4 off to the side, like so, and then I can introduce a 7 down here. If I do that, though, I have to also multiply the top by 7, right? Because these would cancel each other out. And then this 7 can be pulled out here with the 1/4, and this would become 7/4 times sine of 7x over 7x. And so this original limit can be rewritten as the limit as x goes to 0 of 7/4 times sine of 7x over 7x. And then since 7/4 is a constant, we can factor that out of the limit, and this would be 7/4 times the limit as x goes to 0 of sine of 7x over 7x. Now this limit we know is equal to 1 per our earlier comments, and so this just becomes 7/4 times 1, which is 7/4. So you'll be asked to simplify some limits using this property. And that concludes this video lesson.